When you look up at the moon on a clear night, there is just this immense sense of permanence. It looks like this quiet, static silver disk that has, just always been exactly the same, staring down at us since the dawn of humanity.
Oh, absolutely, yeah. It definitely projects this aura of absolute stillness. It is almost like a cosmic museum exhibit that just hasn't been dusted in a few billion years.
Right, exactly. It feels completely frozen in time. But then you start looking closer, and I mean microscopically closer,
Yeah.
and suddenly that quiet silver disk starts looking more like the scene of an ancient apocalyptic crime.
Yeah, because the biggest, most violent events in the solar system are, ironically, often hiding in the smallest microscopic lens. The macro is, it's always hiding in the micro.
Which brings us to the mission for today's deep dive. We're
Yeah.
pulling from a really fascinating stack of sources today, specifically a May 2026 report from technoscience.net that breaks down some, frankly, groundbreaking findings originally published in the Proceedings of the National Academy of Sciences, or PNAS.
Yeah, the core mystery here centers around rocks. But we are talking about very specific basalt rocks brought back from the far side of the moon by the recent Chinese Tianji 6 mission. And the kicker is, these rocks are just fundamentally different from everything we have ever seen before.
Okay, let's unpack this. Because our goal for you today is to explore how a microscopic chemical anomaly found on the dark side of the moon is currently acting as a literal cosmic time machine. It is pulling back the curtain on one of the most violent events in lunar history.
It really is. I mean, the Tianji 6 mission lands on the far side of the moon, scoops up some dirt and rock, and brings it home. And when scientists finally got these basalts into the lab, they found a completely unexpected chemical signature regarding potassium.
A potassium anomaly, right.
Exactly. The potassium isotopes in these far side rocks are notably heavier than any lunar samples previously collected.
And it is so crucial to note that they don't match the samples brought back by the American Apollo missions. They don't even match the lunar meteorites that have naturally fallen to Earth over the eons. These far-side basalts are distinctly chemically unique.
Yeah, the location is the crucial piece of the puzzle here. We really have to emphasize that these samples came from the far side of the moon. That is the key.
Which is such a wild concept to visualize. In our source material, there is this incredible image captured by an earlier mission, the Change 5T1. Have you seen this one?
Oh, the one with the Earth in the background? Yes, it's stunning.
It is. It shows the far side of the moon in the foreground.
Yeah.
Just this barren, rugged, and heavily cratered terrain. But then, hanging in the vast, dark background, is the Earth. It's this tiny blue and white marble suspended in the void.
Seeing our entire world reduced to a distant background object against this battered lunar landscape, it shifts your understanding of our nearest neighbor. It really makes you realize the moon is a world of its own, taking absolute beatings on its far side that we never even see from our vantage point.
And taking hits is exactly what we need to talk about. The specific spot on the far side where these heavy potassium rocks came from is called the South Pole-Aitken Basin. The SPA Basin for short.
Right, and to call the SPA Basin a crater is, frankly, a massive understatement. It is the largest impact structure on the entire moon.
Wow.
Yeah, we are looking at a depression that stretches approximately 2,500 kilometers across the lunar surface.
Let's pause on that scale for a second to really give you a sense of what that means. 2,500 kilometers is, it's roughly the distance from New York City to Denver, Colorado.
Right, just a single continuous crater.
Exactly. We aren't just talking about a stray rock hitting the surface and kicking up some dust. We are talking about a moon-shattering event, a massive asteroid impact billions of years ago that must have nearly ripped the moon apart.
Oh, absolutely. The structural integrity of the moon itself would have been heavily tested by a collision of that magnitude. It's almost unimaginable.
Which leads me to a big logical question here. We know an asteroid hit there. We have a New York to Denver-sized hole to prove it. But how does an impact crater from billions of years ago explain heavy potassium in the dirt today?
That is the million-dollar question.
Right, because a hole is missing rock. How does an asteroid impact alter the fundamental atomic structure of the dirt that is just left behind?
Well, to understand that, we have to look at the mind-boggling physics of an impact at that scale. When an asteroid that large hits a celestial body, it doesn't just push dirt out of the way like a shovel.
It doesn't just dig a hole.
No, it generates colossal heat and pressure.
Yeah.
The energy release is so intense that it literally vaporizes enormous quantities of solid rock. It turns stone into gas instantly.
Wait, really? It just deletes the rock. It flashes it into vapors.
It flashes into vapor, yes. And what's fascinating here is how different elements behave under that kind of extreme rock vaporizing heat. Potassium is what chemists call a moderately volatile element.
Okay, moderately volatile. What does that mean in this context?
It means that while it's a solid under normal conditions, at these extreme temperatures, it transforms into a gas very readily. It wants to evaporate. But not all potassium is perfectly identical. It exists in different isotopes.
Just to make sure we're all on the same page here, isotopes are basically different versions of the same element, right? They have the exact same chemical properties, but slightly different weights because they have a different number of neutrons in their nucleus.
Perfectly stated, yes. Some potassium atoms are physically lighter and some are physically heavier. So during a giant impact, when the immense heat causes the potassium to evaporate, the lighter isotopes evaporate much more easily.
Because they're lighter.
Exactly. They are more energetic, so they achieve escape velocity and are just lost to space.
Okay, here's where it gets really interesting because I want to make sure I'm visualizing this correctly. Is this essentially like boiling a pot of salt water on the stove?
Oh, that's a great analogy.
Right, because if you leave it boiling long enough, the lighter, more energetic water molecules evaporate and turn into steam, floating away to the kitchen. But the heavier salt is left behind in the bottom of the pot.
That is exactly what happens. But instead of a pot of salt water on a stove, we are talking about the surface of the moon boiling solid rock.
Boiling rock. That is such an insane visual.
It really is. The impact created a literal sea of boiling magma and vaporized crust. So the lighter isotopes of potassium boiled off into the vacuum of space, while the heavier isotopes of potassium were left behind.
Concentrated in the lunar crust that eventually cooled and solidified.
Exactly.
There was actually a schematic in our source material that illustrates this perfectly. It was created by Professor Henji Tian, and looking at it really brings your boiling rock explanation to life.
Yeah, Professor Tian's diagram is incredibly helpful for visualizing the scale of this.
It is. The diagram shows this massive gray asteroid, the impactor, striking the lunar surface. And it doesn't just dent the crust. It punches completely through the lunar crust and deep down into the lunar mantle.
It's a deep wound in the planetary body.
And erupting out of that wound, the diagram shows this massive, fiery red and orange splash shooting upward into space. Right in the middle of that fiery splash, the professor has explicitly labeled it volatile loss, with these squiggly arrows pointing out into the void.
Showing the elements escaping.
Exactly. It's exactly what you described. The lighter elements literally fleeing the scene of the impact.
And that fiery splash is what leaves us with the unique chemical signature we see today. The Changes 6 samples show an average increase of heavy potassium compared to the Apollo basalts.
Let's look at the actual numbers here, because this is where I have to push back a little bit. The data shows an average increase of heavy potassium of 0.16 parts per thousand.
Right.
I'm going to repeat that for you listening. 0.16 parts per thousand. That sounds incredibly tiny. It sounds like a rounding error on a spreadsheet. Why are scientists popping champagne over something so small?
I know, it sounds crazy. It is exactly what the French source text wonderfully describes as infime, minuscule, infinitesimal. But in the world of isotope geochemistry, 0.16 parts per thousand is not a rounding error.
It's not.
Not at all. It is a massive, highly significant neon sign blinking in the dark, entirely because of the precision of modern mass spectrometry. We can measure these isotopic ratios with terrifying accuracy.
Wait, let's break down mass spectrometry for a second. Is that basically like a highly sensitive atomic sorting machine? Like it literally separates atoms by their weight so we can actually count the individual heavy versus light atoms?
That's essentially it, yes. You vaporize the sample, shoot it through a magnetic field, and the heavier atoms curve differently than the lighter ones. Because we can sort them so precisely, we know that a 0.16 shift isn't just some glitch in the machine.
Wow, okay.
Yeah, the fact that this shift is uniform across these samples tells a definitive story. This tiny isotopic ratio acts as a literal thermometer and a pressure gauge for an event that happened billions of years ago.
A thermometer and a pressure gauge. Explain the mechanics of that. How does that actually work?
Well, we know exactly how much heat it takes to evaporate lighter potassium, and we know the exact baseline ratio of light to heavy potassium in normal lunar rock.
Okay, so you have your baseline.
Right. And because we know those two variables, this 0.16 difference allows scientists to reverse engineer the explosion. They can look at that tiny number, plug it into thermodynamic equations, and mathematically calculate exactly how hot the impact was.
That is wild.
It tells us how much pressure was generated and the true scale of the collision. It allows us to reconstruct the exact temperature of a rock vaporizing event from the deep past.
So we are looking at a fraction of a microscopic element, and it is painting a picture of an explosion the size of the eastern seaboard of the United States.
Exactly. It's the ultimate forensic science.
Okay, I want to put on my detective hat here for a second. We have a heavy potassium anomaly, and we have a giant crater. But in science, as we always say, correlation isn't causation.
Right, you can't just jump to conclusions.
Just because the heavy potassium is sitting inside the giant crater doesn't automatically mean the crater caused the heavy potassium.
That is a crucial point. If we connect this to the bigger picture of how the scientific method works, you can't just find a piece of evidence, invent a story that fits it, and call it a day.
You have to try to poke holes in it?
You have to actively try to destroy your own hypothesis. You have to test alternative explanations to ensure your final conclusion is actually rock solid.
Right, we have to rule out all the other ways heavy potassium could end up on the far side of the moon. Let's start with the environment itself. The moon is just sitting out there, unprotected by an atmosphere, getting blasted by cosmic rays and solar radiation for billions of years.
True.
So couldn't that ambient radiation just bake the lighter potassium out of the rocks over time? Like a cosmic sunburn that changes the chemistry?
It's a fair question, and the team ran the numbers on cosmic ray exposure. The far side certainly gets bombarded by high-energy radiation from deep space and our sun, and exposure to this kind of radiation can alter isotopes in surface rocks over billions of years.
But does it alter it enough to hit that 0.16 mark?
No, it doesn't. While cosmic rays do have an effect, the mechanism is entirely different and far too wet. Radiation can slowly knock atoms around, but it simply doesn't deliver the concentrated, overwhelming thermal energy required to induce a massive phase change.
So it can't literally boil off that much light potassium.
Exactly. You need immense sudden heat, not a slow, billions of years long sunburn.
Okay, so if the outside environment, the sun and space radiation, didn't bake it away, what about heat from the inside? Because the moon wasn't always dead and cold, it used to be volcanically active.
Very active, yes.
The dark patches we see on the near side of the moon, those man-in-the-moon shapes, those are ancient lava flows, right? Vast plains of basaltic lava. Couldn't the moon's own internal magmatic processes have separated the isotopes?
That is a very logical place to look. Could the churning and cooling of magma deep underground have pushed this heavy potassium to the surface during a volcanic eruption?
Right, because heat is heat, isn't it? If an impact is hot enough to change the isotopes, wouldn't a literal volcano be hot enough too? Why wouldn't magma boil away the light potassium just like an asteroid strike?
It comes down to the thermodynamics of how magma cools versus how an impact vaporizes rock. Think about the difference between simmering a soup for hours versus dropping something into a deep fryer.
Okay, I am tracking with the kitchen analogies.
Good. When magma rises from deep inside the moon, it's incredibly hot, yes, but it cools relatively slowly. As it slowly cools and crystallizes, the atoms have time to lock into solid structures.
So they get trapped before they can escape.
Exactly. The slow cooling of magma doesn't create the violent, instantaneous phase change needed to preferentially lose that much light potassium. It takes a literal flashbang of heat.
A sudden, extreme event.
Yes, an event that whips the light potassium away instantly before it can bond with anything else. The thermal dynamics of lunar magma simply don't produce a signal strong enough to hit that 0.16 parts per thousand shift.
So internal volcanoes are out. The slow simmer doesn't match the crime scene. We need a deep fryer. But that brings me to another idea, and this one makes a lot of intuitive sense to me.
Okay, let's hear it.
If a giant asteroid hits the moon, that asteroid is going to vaporize and leave pieces of itself behind, right? What if the heavy potassium didn't come from the moon boiling away its own rock? What if the heavy potassium was just alien dirt brought there by the asteroid itself?
Right, the impactor melts, mixes with the lunar dirt, and contaminates the crime scene with its own alien chemistry. It's a hypothesis you absolutely have to test.
How do you even go about disproving that? It is all mixed together in the dirt now, isn't it?
You look at the broader isotopic pattern. Meteorites have their own distinct complex chemical fingerprints. If the heavy potassium came from the asteroid, it wouldn't just be the potassium that looks weird.
Oh, I see.
We would expect to see a whole suite of other isotopic anomalies across different elements that match known meteorite profiles.
You'd see a whole constellation of alien elements, not just one isolated thing.
Precisely. But the team didn't find that. The overall isotopic pattern of these Changi 6 samples didn't match the signature of meteorite contamination at all. Aside from the potassium anomaly, the rocks looked distinctly lunar.
Wow. So by systematically eliminating the slow bake of cosmic radiation, the slow simmer of the moon's own internal volcanic plumbing, and the alien debris from the asteroid itself, well, science corners the culprit.
It really does.
We are left with only one viable explanation for this exact isotopic anomaly. It has to be the colossal rock vaporizing energy of the South Pole-Aitken impact itself.
It is the only event energetic enough and specific enough in its thermal dynamics to leave this exact fingerprint behind.
So what does this all mean? Why should you, listening to this deep dive right now, care about a minuscule difference in heavy potassium on the far side of the moon?
It's a great question to ask.
To me, it proves that no event in the universe, no matter how ancient, no matter how massive, is ever truly erased. We tend to think of time as this great destroyer of evidence.
Oh, definitely.
Mountains erode, oceans dry up, craters get buried or paved over. But the most catastrophic collisions in the history of our solar system leave their fingerprints permanently burned into the tiniest, almost invisible atomic structures of the rocks themselves.
It's a beautiful way to think about it.
It is this beautiful reminder that in order to understand the biggest, most violent mysteries of the cosmos, we sometimes have to stop looking through a telescope and start looking through a microscope.
As a scientist, I have to say there is something deeply satisfying about seeing field data perfectly validate our theoretical physics. We've theorized about the sheer violence of the early solar system for decades, but seeing the actual scars of that violence etched into the atomic weight of potassium, well, it makes the chaotic history of our planetary neighborhoods suddenly very, very real.
It completely changes how you look at the ground beneath your feet. Which actually brings me to a final thought I want to leave you with today.
Oh, I'm curious.
Well, we've just spent all this time talking about how a massive impact billions of years ago fundamentally altered the chemical signature of the moon's crust by flash boiling away elements. It leaves you wondering. Earth has been hit by massive asteroids too, right? Our planet has suffered impacts that dwarf our wildest imaginations.
More times than we can count, especially in the early days of the solar system.
If that kind of catastrophic energy can permanently rewrite the isotopic signature of a lunar basin, what undiscovered microscopic anomalies are hiding right beneath our feet here on Earth? What tiny invisible elemental clues are buried deep within our own planet's ancient eroded impact craters, just waiting for someone to find them and completely rewrite the history of our world?